Hello, this is Chris Regan with the Federated Botnet Attack Detection. So I worked with Dr. Parisi mainly as my primary advisor on my GRA slash thesis work here. Yeah, this paper was also, this research was funded by SunTrust and Altruist. And you can see there the annotation there for the Cybersecurity Information Fund. Not able currently to present the actual working code for the material. It's still under NDA at the moment. However, we can talk about the process of what it is and how it exactly goes about and works. The botnets, you never know when they're going to detect. They're dynamic, they're unique, and they're really unusual half the time when you're working to detect them. However, you want to use traditional network traffic to actually attack modern current systems, you're going to have to use similar techniques that we've seen in the past. So we can train on public data sets and still actually get a better idea of what a production result it will look like. So we have the idea that we can take the source IP, the destination IP, and those other sort of package headers, and we can boil those down into statistical features, capture them within a particular window or time frame, and that can be changed and addressed for any particular need. And then you can train your model to identify benign traffic, good positive data. So we train primarily on this benign traffic and normal data, as we might well call it. We do that first initially because we're using a deep autoencoder. The autoencoders become very sensitive after they're thoroughly trained. Like on some machine learning types, there might be supervised in a way they train on both the wrong data, or maybe they train on just the right data. So in this case, we're training on just this correct data initially, because when we detect these anomalies, we'll actually be sensitive enough to those changes that our accuracy becomes fairly high. And so we have the ability to then distribute that process in a federated manner. So federated computing, or federated learning in this case, and it will also be part of decentralized computing. So this is indicating that we take the process of the machine learning and put it on devices near the network edge. When you take these devices to the network edge, that allows you to maintain data security by not moving it off premise. That's a core component that makes machine learning fairly difficult today, especially in medical areas or in IT fields, because those security vulnerabilities exist when data is moved. We can now say, hey, you control your computational performance, and you control the machine learning process, and you control your data. So instead of just saying, oh, we need the data on this side where we can compute it and actually work on it, we can now move it to where those networks are, because devices have on the near the network edge, like network switches or routers, or even additional devices. They can be even like a computer that's in the room that's routing the network traffic to these IoT devices, like your Alexa, your cameras. So you route them through these devices like a Raspberry Pi or Arduino, or pre-existing devices on the network, and there the computing computational work can be done. This is because we're dealing with very small pieces of data, particularly in these botnets. They're not doing large data. Their main attacking methods are large quantities of small data that need to be handled, or they're trying to do packages from attacks from one internal device to another. So those have unique properties to them that are just not there in normal traffic. So that becomes our main core component of detection, and then we're bringing that operation of federated to the local network. So you have this internalized security system that can detect these types of attacks. They can be anywhere, your botnet attacks, they can be your DDoS type of attacks. Because these attacks have these weird properties to them and they get detected easily, we have very high accuracy. We're touching 98, 99% accuracy in these cases, and we're just able to accurately detect, have data security, and we're just able to have this pipeline that can also be deployable in a modern environment. And because it's also federated, you maintain your own models. So these models can be hosted on the local network, and they have device type specifications to them. So if you have a bunch of cameras, you can then have a model set up that a machine learning process would take from a server unit, and it would then pull that server unit would then deliver to the device requesting it, which that server can probably live off network because the models themselves are not important to the actual machine learning after you're doing training. So the importance of it are not as high as the actual data, because if that model gets confiscated in some way or gets data mined, it's like, all right, that model is only important when you're doing the machine learning process itself, and you wouldn't be able to do anything with it. So that's the part where we're okay with letting this device get moved off network and just having it, that's the part where we can actually sacrifice the potential vulnerabilities, where the data itself is the actual important component. So the process, IoT device has internet access, and all the data is port mirrored. So we just port mirror that data as it goes through, and we're not actually worried about it, the model where it actually goes. So we have a server that will then aggregate local models. So on your local network, your on-premise network, you might have different areas of the office that need different devices, and they can then themselves aggregate their models together to then improve performance over time. So this system can actually remain disconnected from the internet itself and still actually properly protect the devices that are on that network, where like the main upgrading wouldn't actually be at the software level as much as it would be at the hardware level. You would get a new software in, and then you would probably train on some new data, or there potentially could be a chance of having repos for models that are trained on other locations, and it would be internally done. You could do that internally, and these models are really small packages. They don't take up a lot of network traffic, and that wrapping that whole package together allows you to have this self-sustaining system that is also living on your network. You control it as an individual or a company, and so you are protected by the device that you have access to. You don't have to worry about necessarily updates from external sites, but that allows the system to maintain itself, grow, learn, and also be energy efficient, because you're not dealing with the high level network, you're dealing with near edge network, so it's not operating that full mega capacity at the whole time. So we actually have this reduction of use, because IoT devices, we're not expecting them to be used constantly all day, all night. It's not like the camera is gonna, if a camera is sensor based, then you only it only has the network traffic going in and out of that camera when it flags its sensor. Or if you have some other light sensors, or if you have any other environment sensors, those are only working certain times a day, which also become part of its training process. But I hope this presentation worked well for you guys. And if you have any questions, we have the contact information over here. And thank you for your time.